right, guys, welcome back to Gen Chem. We're going to do some more review on collision theory today, and we're going to start looking at energy diagrams and learning how to use those to understand what's happening in a reaction. So I just wanted to review the basic concept of collision theory because it's really important that we understand it so that we understand what it takes to have a reaction happen. So the main idea of collision theory is that in order for things to react, that the molecules involved in the reaction have to collide. They have to physically come in contact with each other, okay? Now, in order to react, colliding isn't enough. Not only do they need to actually come in contact with each other, they have to have that collision have two things. The first thing is that collision has to be on the right part of both molecules. So if you are colliding the molecules together on the wrong parts, the part of the molecule that isn't really involved in the reaction, that's not going to cause a reaction. So you have to have a reaction where the molecules collide on the correct or the proper orientation of both of the molecules. The other thing that we also need to have for these atoms, ions, or molecules to react, we have to have the reaction or that collision happen with enough force so that we have enough energy to make that reaction happen. Now, that energy that it takes to make a reaction happen is what we are making and breaking bonds. We're breaking bonds of the old molecule or the old reactant, and we're making new bonds of the products of that reaction. And making and breaking bonds takes energy. So we have to have that collision hit hard enough that we have enough energy to do that. So that is collision theory in a nutshell. Okay, so now I want to go and we're going to look at the energy diagrams that we have when we have a reaction. So here's a very basic energy diagram, and I'm going to show you another one as well so that you can see what's going on. I'm going to make this big for a second, okay? So I want to put some lines in here so that we can see what's going on. Notice that X does not go all the way down to the bottom. Notice X goes right to where this P is, okay? So let's do some notes here. So R, right here, this is a symbol for reactants. And I cannot draw today or write reactants. Okay, so you'll notice that on this Y diagram, we have PE. What does PE stand for? It stands for potential energy. So this is the energy that we have in the bonds of the reactants and the products and everything else in between as we go through this reaction. On the X coordinate, we have what's called the reaction coordinate. This is really time. So we're starting at time 0 until the reaction is finished. Okay, so this is just time going forward. Sometimes it would be really fast. Sometimes it's really slow. Sometimes, we'll have minutes, seconds, even nanoseconds, depending on what's going on. This potential energy on the the y-axis is usually given off in kilojoules or joules. Okay, that's just a unit of energy that we use in the scientific community. So a joule is how much energy it takes for something to happen. Okay, so another thing that I really want to orient you here, the R stands for reactants. We've got a P here. This stands for products. Okay, so there's the orientation I want to show you and tell you what some of these lines mean when we're talking about these reaction diagrams. Okay? So I'm going to put in a couple of things to help you understand what's going on. Notice that this line X here is the difference between the reactants and the products. Anytime I'm looking at the difference between the reactants and the products, this is what we call the enthalpy, or the energy of the reaction. We symbolize this. So that's the enthalpy of the reaction. We symbolize this with a delta H. So that's the heat, or the enthalpy of the reaction. Notice in this reaction, my products here have less energy than my reactants. That means my overall change is negative. I went down in energy. So if delta H is negative, that means I have an exothermic reaction. That means that energy is given off. Look at all this energy that was given off. So energy is given off. So these reactions are going to feel warm or even hot, okay, because energy is being given out into the rest of the system, okay? So X here is my delta H, or the enthalpy of my reaction. Now let's think about this. What if delta H is positive? What if my products have more energy than my reactants? I have to put energy in to get to those products. I have an energy hill to climb. That means that this is an endothermic reaction. So energy is added. So endothermic reactions end up feeling cold because they suck energy in from the rest of the system to feel and fuel that reaction. These feel cold. Okay. So if you've ever used a heat pack or an ice pack, that ice pack, because it feels cold as you're shaking up those chemicals in that instant ice pack, that is an endothermic reaction. Okay. Let's look at this next line here. Notice that Y goes from the start of the reactants to the top of the energy curve. So that difference between the reactants and the energy curve, this is my activation energy. This is the energy it takes to make this reaction happen. So it's the energy it takes to make the reaction happen. If I don't put that energy in, even though this reaction on this graph is exothermic, it's releasing energy, if I don't put this energy in, we don't have the energy to break those bonds of our reactants and start forming the bonds of our products. It takes energy to have a reaction happen, even if that reaction is exothermic. Okay? All right. And then notice I have Z. Sometimes we will read these energy diagrams going backwards. Notice Z is the difference between where we would start if we were reading this backwards and the top of the energy curve. So this is the activation energy of the reverse reaction. Reverse reaction. And yes, almost all reactions are reversible. So notice when I do this reaction backwards, my delta H is still the same, only this time it is positive. And so, that really didn't let me write very well, did it? With that big fat marker. So this way, my delta H is positive going backwards because I'm putting in all this energy. So that would be an endothermic reaction. Okay. Now, I also want to notice what we call this area right at the very top of the energy curve. This at the top of the energy curve is what we call the activated complex. Okay, that activated complex is kind of the in-between molecule. It's the molecule where we're breaking the reactants bonds and we're starting to form the products bonds. So we have these really weird molecules that are kind of in between both the reactants and the products. We have all kinds of things being created and destroyed all at the same time. And because of all that creation and all that destruction in the middle of that reaction, that's why that is at the highest energy area, because that is where all that energy for that reaction is being used to go from the reactants to the products. Okay? All right. So let's look at a couple other things in this reaction as well. Okay? Notice I have this area between where the reactants are and the bottom. That between where the reactants and the bottom is the potential energy of the reactants. Okay, so the reactants, we can measure how much energy is stored in those bonds. We can do the same thing for the products too. That's going to be right here. Between the products and that baseline, that is the potential energy of the products. Okay, so that is how you read an energy diagram. Now there's one more thing that when we would put a catalyst in, we said that catalysts speed up reactions. How do catalysts speed up reactions? They speed up reactions by giving an alternate pathway. And so if I put in a catalyst, I would have an alternate pathway at a lower energy level. So I'm going to put a catalyst pathway in a dotted red line here. I would still need to put in some extra energy, but this catalyst pathway, if you notice, is less energy than the uncatalyzed activated complex. My activated complex is a lot lower with my catalyst, which means a lot more molecules are going to have that energy to actually complete that reaction. And because more molecules have the energy to complete that reaction is going to appear to go faster. Okay, so the line drawing a catalyst is just our dotted red line. Now, we did say at the very beginning whether I said this was exothermic or endothermic. Remember, we have a negative delta H when we're moving forward. So this is an exothermic reaction because our products have less energy than our reactants. Now, if I was reading this backwards, looking at the reverse reaction, where our product side would actually be our reactants, notice we have to actually put energy in. And so if I was doing the reverse reaction, this would be endothermic on the reverse. Okay, so let me show you on yet another diagram. Let's just look at this next diagram, and we're going to put in some things on this one as well. Okay, so what do you think A represents? Do you have an idea from all the things that we looked at? A is, let's see, I don't want this pen. Let's do a better pen and let's make it thinner because I don't want it that thick. A is our potential energy of our products or our reactants. So this is our potential energy of our reactants. Okay, that's A. B, what do you think B is? Yeah, that's the activated complex energy. So this is our activated complex energy. And it's not going to let me. That is B. Okay, so what is C? This is my delta H. That is the enthalpy of my reaction. Is it positive or negative? I have to put energy in to get to the end, don't I? So this is positive. So is that endo or exothermic? It is endothermic. Okay, what is D? Yeah, it's my potential energy of my products. Okay, now there's a couple things that are missing on this diagram. We actually don't have a line for our activation energy. So let's put that in really quick. I'm going to put that in orange. So if I go from my reactants to the top of my energy curve, this is my activation energy. Of the forward reaction. Okay. Now, can I do the activation energy of the reverse reaction? I sure can. Now, activation energy is also shorthanded as E sub A, like this. So let's do the reverse. Let's put that in green. Reverse, we're going to pretend like this is our reactants and this is our products. So our activation energy of the reverse would be this. So this would be our activation energy, or our E sub A prime. So this is reverse. Okay. So there's all kinds of things that we can get off of these energy diagrams. We can see how much energy products have. We can see how much energy reactants have. We can see how much energy a reaction takes to take place. We can see how much the activation energy is, how much force that collision has to have in order to create that activated complex, which is up here. Remember, the activated complex is up at the top. A lot of these will have actual scales where you can actually see how many kilojoules and read the graph. And it's a way that we can actually understand what's going on in the reaction. So have fun and enjoy. And if you have questions on reading these graphs, come and ask me a question or email me. Thanks. We'll see you. Bye.